Hi, I'm Alfonso Lagares, a student in Professor Fenton's Physics 2211 class, and this is my Lab 1 report where I'll be studying the motion of an object moving at a constant velocity. First, I'll introduce the concept of rectilinear motion and why it is important to understand, and then I'll explain how I collected this lab's data using Tracker and a computer model in Python. Then, I'll analyze and discuss this data, and finally, I'll give a short conclusion and evaluation of the lab. This lab focuses on objects that move at a constant velocity. In other words, objects that undergo rectilinear motion. This means the object follows a linear trajectory in which its velocity remains constant, which implies that its acceleration must be zero. Following Newton's second law, this means that the net force acting on the body must be zero. At the same time, we know that the change in momentum of an object is equal to the net force acting on it. Thus, the change of momentum of the body must be zero for it to undergo rectilinear motion. This does not mean that there are no forces acting on the body, it just means that the sum of these forces equals zero. Understanding this type of motion is extremely important, as it is a great example of the principles of momentum and the implications of Newton's second law. Not only that, but every object follows rectilinear motion if forces are not applied to it. From subatomic particles to asteroids, if the net force acting on an object is approximately zero, their movement can be accurately described following the equations derived from this motion. In order to understand this type of motion, I used Tracker to extract data from a video of a ping pong ball rolling on the floor. In this case, the studied system consisted of the ping pong ball, the floor, and the earth. I rolled the ball and then recorded its position over time using Tracker, trying to keep the camera perpendicular to the floor and the wall in order to avoid parallax error. These data was then imported to Excel. The ball seems to follow a rectilinear motion, so the equations of this type of movement were used to create a model for the ball's movement. Going on to the model, I used GlowScript to simulate the ping pong ball's movement. The ball is represented by this ball object, and a trail and origin are assigned to it. The system is then given a mass, which for the ping pong ball is 2.7 milligrams, an initial position at the origin, and an initial velocity. This velocity is in the positive x direction and was taken from the average velocity of the ball in the tracker data. An arrow representing the velocity vector is also added. The simulation is run for 2.3 seconds, the time the ball is in the frame for the video, and the ball's position and velocity are updated using Newton's second law and the equations of rectilinear motion. The result is this animation of the ball traveling through space, plots of the ball's position and velocity, and the actual position data. This data was then exported to Excel in order to study it more closely. Comparing the observed and predicted position of a ping pong ball, we can conclude that they are close enough to say that the model is accurate at predicting this kind of motion. Furthermore, we can see that in the observed motion, the ball has a slightly higher initial velocity, and then slowly slows down, getting closer to the predicted motion as time advances. This is probably due to the friction force between the air and the ball, as this force would slow down the ball as it travels. This force is small enough that it can be ignored, and thus the model assumed the total force acting on the system was zero. In order to make the model more precise at predicting the ball's position, I believe friction should be included in the forces acting on the ball, and its slowing effect should be accounted for. In conclusion, the observation and model produce similar data, but the model's accuracy could be improved by including the friction force the ball experiences. If the x-axis had been flipped in the observation and the model, the position of the ball would be decreasing in value and not increasing, and so its velocity would be negative instead of positive. The position graph would thus have this shape, with the same slope as the actual position graph, but in the negative direction. It is difficult to reconstruct the total forces acting on the ball as it is rolled on the floor, as we only observed the net force on the object, which in this case was close to zero. What is true is that we can establish at least three forces acting on the body: the force of gravity, due to the ball's mass, the normal force the ground applies on the ball, and a small air friction force, which opposes the ball's velocity.